modular, so it has point feet, the feet that we use with the formal methods, so articulated feet. And we also have spring feet to understand compliant behavior in robots, and we can change these different things up. So Wenlong will turn it on, run it, hopefully it walks, and talk about it a little bit too.
Changing speed, it's able to adjust itself to the new speed. This is a two-dimensional robot, meaning it can only walk in a sagittal plane, up, down, and forward, backwards, not left, right. So after we're developing, this is our fourth generation of this robot, and after all the fourth generation, we're making this platform very reliable, so that we can play some very new, novel controllers that we don't know that work on more complicated or not. And then we can just use this as a verification to test those controllers. But the robot is very modular, so we can easily swap all those legs on the robot, and by clicking some buttons on the software there, using LabVIEW, to easily switch to a new different controller to do new configurations. So far it's been very robust, and the longest record of this robot has been walking for 3 hours on its own.
So this is the robot that Paulo mentioned we're starting to put the formal methods on as well. So we're trying the model-free, model-independent things, joint by joint, and all joined together. So again, the nice thing about this robot is simpler because it's planar, but this really lets us get to the core of what's at the system level and try these different fundamental things and change them out, change out the leg configurations, and really explore the sort of the fundamental science before we graduate things to the next generation robot, which is 3D walking robots. So this is our third generation prosthetic. The one in the videos you saw, we demoed this one for DC and for Congress actually. We're currently building our fourth generation prosthetic, which is a little more svelte, a little more compact and optimized. So this one's kind of at the end of its life, but we're still going to demo it and hope it goes okay as well. Rachel is actually an NSF fellow. She just received an NSF fellowship this year. And so this is the beginning of her PhD work on doing robotic assisted devices. So she's going to see if she can show it off a little bit. We'll cross our fingers. Very good.
That's good.
Yeah,
Good.
that is good. So we actually generate gates for this device the same way we generate gates for humanoid robots. We actually generate the gates in 3 dimensions using stuff that Jesse will talk about later that Younga developed when he was in my lab as a PhD and is now being implemented on robots at Michigan. The same thing for the gate generation is applied here. The difference is we don't have a whole robot, so we have to actually simulate this device in conjunction with the person, which we can do in simulation. And then when we put this stuff on the device, we have to read feedback from the person to the device. So the device is sensing through an IMU her motions and reacting accordingly. According to HED, it's going through the phase variable based on what it's sensing in the person. So, want to do one more walk?
All right.
It's not easy to walk in though.
Yeah.
That is a hard thing to learn.
Yeah.
When will you be ready for 2 robot legs?
I've given that exact challenge to her, actually. I said she should wear AmPro 3 and AmPro 4 at the same time, and then she gets a PhD. So why don't you tell us just in 1 minute about what you're doing next with this and what you're thinking about?
Yeah, so next we recently got a 6-axis load cell, which we put between the foot and the ankle to measure the torques and forces there. We could use this for force control or also for more sensing of terrain. And then, then with the new one, that one is adjustable. And then there's like the postdoc working on like developing like a pressure sensor that we could do pressure mapping out the foot or track the center of pressure to make the gait more symmetric.
So we have a new postdoc that comes from the soft materials world. Another professor, Chiara, was his postdoc advisor, or sorry, a graduate PhD advisor. And so we're trying to develop smart soft sensors to put in the feet so we can enhance this feedback between the device and the person.
Have you ever tested this with on a real RPG?
Not this one, but we put our previous generation on a real MPT. Yeah, and they walked really, really well. It was easier for them to walk than my grad students.
That's what I
So the attachment we use is actually the same attachment they use for prosthetics. So it hooks right onto an existing device, their socket attachment. So that's a lot easier. This is kind of loose by comparison, so it's much harder for her to walk in this, and she has her leg. Unfortunately, or fortunately. Fortunately. No, but it is difficult to walk in this. So, but it gives us a good way to test things out and make sure they're proven before we bring them to the actual user. So, all right.
When
good.
you're learning the gait, is that for the specific person, or is that more general?
So that's a good question. So we can generate gates subject by subject. So basically we can take the parameters of the person when we do the gate generation and then generate new gates using this optimization framework for gate generation that we have. And actually this is exactly what we're doing for the exoskeleton, the couple clips I showed you. Every subject gets a new gate for the exoskeleton. It's the same general paradigm as what we did for the prosthetic, with some differences because it's a full body system. Right? But yeah, so we can make subject specific gates. Of course, that might not get you all the way there. There's still comfort conditions, just like when you're driving a car, right? There's certain things that the subjects like when they're using a prosthetic. So we'd like to see how we can fold those in with barrier functions and potentially some machine learning, right? So how do we sort of online modify to make sure we're safe and we optimize the comfort of the patient and we adapt to new terrains. So all the things we're doing on bipedal robots ultimately will translate to this device. Great.
How long does the battery last?
3 or 4 hours. Yeah. We've actually walked a mile in a previous generation and only used 20% of the battery, and we've gotten better since then. So we get good battery life. Okay, great. We'll go to the next demo. Come back, by the way, all these are meant to be after we do the kind of demos. Come back and talk to the students for a minute, please, because it's their work that makes all this happen. So the goal is how do we make something like this hop 6 feet in the air, or 2 meters? It's a hard problem, right? So the time you're in contact with the ground, meaning the time when you're controllable, is about 0.03 seconds. So in 0.03 seconds, you have to make all your control decisions, and then you're in the air. So how do we get this sort of very dynamic maneuver? So again, in the way we do things in the lab, we're going back very simple with a 1D hopper to really focus on the fundamental science, and we're building 2 designs with 2 different hopping mechanisms. This one is actually a clutch mechanism, so we pull in the spring, and then we clutch it and release it. The other one is going to be, which isn't quite built yet, is going to be a moving mass model. So we're going to move a mass around. So this will be kind of the continuous and discrete, and we're going to see which of these is more efficient and gives us better jump heights as this sort of comparative metric. So just give you a little bit of idea on the hardware we're building now. And again, all these things, it's worth saying. So for example, Eric here designed and machined everything from scratch here. So this is a complete, we don't outsource anything, which is a source of headaches sometimes. But the prosthetic, everything we build in-house. By our students, which I think is an important exercise, albeit time-consuming sometimes. Nothing remains of the original Segway but the motors and the chassis. So what he did is at every level, the motor controller, the CPU, the sensors, everything is custom inside this aluminum thing, which was also machined here, designed here. The idea is if we're going to do safety-critical software, we can't just put it on top of something. We have to understand every single stage of implementation in the real time. And so this is an exercise in that, especially in the context, again, of safety critical. I showed you the kick. We're not going to do the kick today because we've just redesigned this whole thing, actually, for Gen 2, essentially. But he's going to drive it around and show you, the algorithms in action a little bit. So let's hope. You might want to steer clear. Yeah, take up the perimeter. Yeah, I never predict what robots do. We're not totally safety critical yet. Yeah.
So we're in the middle of redesigning essentially all the electronics and the software, because so far all the math is with ideal system, and we're interested in how do you have more realistic hypotheses like model uncertainty and all the implementation. We think how do we take all the complexity of implementation, put that in the math, and then how do we implement it rigorously. So right now it's just a simple controller, and so we've developed all the algorithms, the interfaces, and so we have like feedback, and we can basically do anything we want with it. So right now it's in a moderate state of working, but that doesn't mean just stopping.
We're going back to the basics. We're connecting with simulation, with the software at every level to really understand the system is the ultimate idea, right? Are you going to run it again? Or?
Yeah.
Let's drive it around for 1 second just to hopefully not hit anybody. And by the way, that stack for weights at the top are so we can modulate the weights on it and unmodeled weights and understand disturbances. So what he's working on is this robustness of the barrier to unmodeled dynamics and everything else and make sure we guarantee safety at the same time.
And the goal is to ride it afterwards. If you just remove the column, we can just ride the same.
Yeah, ultimately we want to ride it, but we're not quite ready for that step yet. So, all right, very good. Okay, good. Very good. Thank you, Thomas. So some backstory. We just got this robot in the lab, 3 weeks ago now? A month ago, maybe? This is one of 3 that were built. There's another one at Michigan. So wait 1 second to start so I can, people will be distracted by the robot. Yeah. So there's one at Michigan and there's one at Harvard. Of course, Michigan and Caltech are going to kill it on the robot. So right now, this is not our stuff. I want to make that clear. This is not our algorithms at this point. This is Jonathan Hurst's sort of hierarchical algorithms on this robot. But the point of the robot is that we can put our own stuff on it. And it's a platform that's meant to be robust to outside. So the videos you'll see of it outside, for example, it's been outside and when it fell, that video you saw, this is the scar. So, but it didn't stop working. So the idea is we build stuff, but we can't really take that stuff outside. It will break. I mean, it's a different robustness. But a professional company built off of a professor that builds really good hardware gives us that robustness, and we're going to put our custom things on it and understand safety, understand barriers, understand gate generation. All the things we're talking about today will ultimately filter to this robot. And just to put context to that, I had lunch with Jonathan a couple weeks ago, and he said sort of his hierarchical algorithms, they're very impressive. You'll see it. It's really pretty. But this is the best he can do. So he even said this. He's like, this is all we can do. We can't make it do anything else. And that's why, he said, that's why I need you guys, meaning Jesse and I and everyone else, is can we extend beyond with formal mathematical frameworks? And that's what that's the mantle, the challenge that's been cast. So we hope to be able to do that. So with that being said, I'll stop talking, so show off the robot a little bit. So you can walk it maybe this way.
Yeah,
A little walking.
try to get a good direction to point it.
It's terrifying for me to see a robot without anything over it. You know, it's a new experience, which is really cool because it says we can start really playing with robots, right? It's pretty cool. So where's Xiaobin? So why don't you? So maybe spend 30 seconds telling him what you're going to do, Xiaobin.
Okay, so before I was working on granular terrain, work on stable terrain, and later was 2D robot. In the future, we're going to make it happen on CASI and using all the sensing capabilities on the robot to understand the terrain we are working on, and then generate gates and ensure safety from it.
Well, we got some turf to start to play with different terrain. So what we're actually doing is even with Jonathan's controllers, we can look at the different reaction forces in the robot based on what terrain it's walking on.
So this thing.
So just looking at the reaction force of the robot, you can really see the difference in terrains. I mean, it's very dramatic on at the force level. So trying to understand that going forward will be the key. In addition to just those things, the other challenge is sitting at this treadmill right here. So this treadmill can actually go 40 miles per hour. I kid you not. Wow. Usain Bolt runs 27 miles per hour. So you can see where we're going here. So can we make a robot run faster than Usain Bolt? This is the place we're going to try to do it. You notice all the support structures in the ceiling. These are more than just decoration, right? These are to make sure we can really get these robots going and make sure they don't blow through the back wall, right? So that's, for example, Wenlong is working on running on CASI as we speak. We have some in simulation. We hope to try it on the robot fairly soon. And Jake, why don't you just kind of talk about what you're doing quickly, and then...
Yeah, my last project was working on the Duris 3D humanoid robot, which is playing on all the screens. And so kind of what my task is right now is taking a lot of the methods that we implemented on the Sturus 3D humanoid robot and translating them to our Cassie biped. And then from that working on essentially stabilizing our walking gaits that we're generating in our optimization methods.
So it's really about formalizing this translation to hardware. This is a big thing in this lab, and you find this to be more and more acute when you go to more dynamic behaviors like running. So what's the gap between the models and the real world, right? We're seeing this on cars, we're seeing it on robots, but it's a universal thing. So, okay, great. Well, thank you, the students, for doing the demos. So I'd like to encourage everyone to spend a few minutes, walk around the lab, talk to the students. We'll turn on the robots so you can come see them close up in person while you interact, okay? So with that, thank you very much.